Welcome back. This is chapter 16 on temperature and heat. And in this video, we'll look at section 16.3, heat transfer. And in this section, we're going to look at the three main heat transfer mechanisms, and we're going to solve some problems involving those three mechanisms. So let's get into it. The first heat transfer mechanism that we'll look at is conduction. Conduction is heat transfer through direct physical contact. It occurs as molecules in a hotter region collide with and transfer energy to the molecules in an adjacent cooler region. So you look at this diagram that I have. This is a substance. You can think of it as a slab. Maybe it's a wall, but it's some material that heat is going to transfer through. And you'll notice some quantities with this. We've got a cross-sectional area. So you can think this side that we're looking at here, this is one side of the material, and then the other side is facing away from us. So that's the cross-sectional area through which the heat is going to transfer. We can measure that in square meters or square centimeters or some area. You can also see delta X. This is the thickness of the material through which the heat is going to transfer. Now, the way I've drawn it, and I've copied the picture that's in the book on page 300, we have the far side and the near side. And the way I've drawn it, the far side is the hotter temperature. So you can see it's T plus delta T, as opposed to the near side is the lower temperature T. So the difference in temperature, that's what's going to be important for the equation, is that delta T. And if the hotter side is on the far side, then that means that heat is going to travel, as you can see with this green vector here, that's h, the rate of heat flow from the far side to the near side. Now, I've drawn it as it's written in the book, and you can see the x direction is the direction of increasing temperature. So that's the direction of increasing x as well. And it's drawn away from us or towards the far side. That's not really that important, but what it does is it establishes and helps us to understand why in the equation below there's a negative sign. However, the reality is the way we're going to be approaching the problems in this class, we're not going to need that negative sign. The negative just refers to the direction of heat flow. It's going in the negative x direction because it's going in the direction of decreasing temperature. However, we in this class, you will just be concerned with the absolute value of this expression, so you're not even going to need that negative sign. So there's the equation as it's given in the book. H, which is the rate of heat flow, is equal to, and again, we're just going to ignore that negative sign, K, which is called the thermal conductivity of the substance. And that's shown in the table that is on page 300, times the cross-sectional area, times the difference in temperature divided by the thickness. So let's think about what each of these parts mean. The rate of heat flow, how fast heat flows from one side to the other, has something to do with the substance itself. That's K. And if it is a conductor, a thermal conductor, such as some kind of metal, it's going to be a high thermal conductivity. Also the area, the greater the cross-sectional area, you're going to have more heat flowing. The temperature difference makes a difference. So the hotter it is on one side versus the cooler on the other, you're going to get more of that rate of flow of heat. Divided by the thickness, so the thicker the material, the more insulating it is. The thinner the material, the easier it is for heat to get through. So some examples of insulators versus conductors, and you can see the full table, again, in your book. It's table 16.2. But air, for example, with a very low thermal conductivity is 0.026 watts per meter Kelvin. Fiberglass, another good insulator, is 0.042 watts per meter Kelvin. And we're going to contrast that with good conductors, typically metals. Copper is 401, iron is 80.4. So as you do the homeworks, when you're working such problems as this, just refer to the table for thermal conductivities as necessary. There's the table that's in the book. You can see all of those and refer to it. Let's look at an example. Let's look at the heat loss through a window. Now this window in my example has an area of 4 square meters and it's 4 millimeters thick. Let's say that it's 0 degrees Celsius outside, nice winter day, and it's 4 degrees Celsius inside. Now, you might think typically in a house it's going to be warmer than 4 degrees Celsius. You probably want to keep it at room temperature, maybe closer to 20 degrees Celsius. But we're not concerned with the temperature inside the rooms of the house. What matters is the temperature on the other side of the window. And on the other side, on the inside of the window, right there at the window, it can be pretty cold. And you can test this on a winter day when it's nice and cold outside. It might be nice and warm in your house if you have the heater running, but touch the window itself. The window, the area near the window can be very cold. And so it's not going to be that much warmer than what it is on the outside. So we'll put a typical value here of 4 degrees Celsius on the inside. And I want to know what is the rate of heat flow. There's the diagram as I've drawn it. Inside it's 4 degrees Celsius, outside 0 degrees Celsius. Heat, of course, is going to flow to the right. The rate of heat flow there, I'm emphasizing the absolute value. I'm not going to care about the negative sign, but it's a window made of glass. And in the table, it says glass, its thermal conductivity is somewhere between 0.7 and 0.9. Well, I'm just going to give it a 0.9. We have 4 meters squared times the difference in temperature, 4 minus 0, divided by the area. And so we have 4 times, we're dividing by the thickness, there it is, 4 millimeters, which is 4 times 10 to the negative 3 meters. And that gives us 3,600 watts. So through one rather large window on a winter day, think about that, there is a heat loss just that goes to the outdoors of 3,600 watts. Now you compare that with 100-watt light bulbs, pretty bright incandescent light bulbs, 36 of them running all the time. That's pretty significant. Now, in 24 hours, 3,600 watts times 24 hours, that is, over a 24-hour period, 86.4 kilowatt hours. Now, at the time I made this slide, I used a rate of, for the power company charges about 10 cents per kilowatt hour. That's changed a bit over the years, and now you can count on that being 30, 40, maybe as high as 60 cents per kilowatt hour. So whereas I wrote $9 there on the screen, think of that as more like maybe closer to $30, maybe even $40, at least at the current rates in California. So that's a lot of loss through the windows. Now, so we find ways to make more efficient windows. We can have thicker windows, but also we have what's called double pane windows. A double pane window means there's the glass and there's another pane of glass, but in between them is air, and air acts as a good conductor. Air acts as a good insulator, keeping that heat from transferring. Now that brings us to the next topic. What if we have multiple layers? And so you look at the bottom of the screen, and let's think about multiple layers. This is just 2 layers here with different thermal conductivities. So let's say in this picture that heat goes from region, what I'll call region 3, so it's at a higher temperature of 3, and it goes through to temperature 2, but then there's another layer of some other substance, and ultimately to temperature 1. The book does not give an equation for this, but the book does take us through how to figure this out. And we'll see what is the rate of heat flow when we're dealing with these 2 different materials, or maybe with 3 or 4 or 5 different materials, such as a double paned window has glass, then air, then glass. A triple paned window might have glass, air, and glass. We're looking at 5 different materials. Now, first we need to recognize, as it says here, that the rate of heat flow must be the same in both materials. You're not going to have much heat flow through one material and then a decrease in heat flow through the other, because then you would get a buildup of heat in the middle. And you certainly can't have a little bit of heat flow through the first material and then a lot of heat flow through the second material, because then you would have heat that gets invented in the middle. So it has to be the same rate of heat flow. So here I put two of these equations together. The rate of heat flow, which is the same, is, and again, I'm going to ignore that negative sign, but I've written it out for you anyway. K1 area times T2 minus T1 over delta X1. That takes care of the rate of heat flow through the first material. And it's equivalent to K2 area, we're assuming the areas are the same, T3 minus T2 over delta X2. And that covers the rate of heat flow from T3 to T2. And we want an expression for rate of heat flow as a function of T1 and T3, and we really don't care what T2 is. That's just an intermediate step. Well, to make the algebra easier, it's going to be useful to introduce a new concept called thermal resistance. R equals delta X over Ka. And you relate that to the equation above, and it has to do with the reciprocal of parts of that equation. And not only is thermal resistance useful because it will get us through this problem, this mathematical problem here, but also it's useful, it's a quantity that's used in the industry, in the insulation industry, and we'll get to that soon. So the equation that we had becomes H equals, and again those negative signs that are going to go away, T2 minus T1 over, and all of those other terms just become over R1, equals T3 minus T2 over R2. Now, the first bit, which I will circle in blue, there we go. We're going to make an equation out of that. Multiply both sides by R1, and we get R1 times H equals T1 minus T2. The second bit, when we relate H to this part right here, we get a similar equation, R2 times H equals T2 minus T3. Notice I've set them up in such a way that I can do addition of those two equations. And look what happens. On the left-hand side, it becomes HR1 plus HR2. Well, let's simplify that to H times R1 plus R2 equals T1 minus T3. As I mentioned before, the T2 goes away. That's okay. We really didn't care about T2, that temperature in the middle. And what we're left with is H equals T1 minus T3 over R1 plus R2. So this means that the rate of heat flow is the difference in temperature divided by the sum of both of the thermal resistances, delta X over Ka. Now, an industrial application of this, we think about insulation that's in the walls, in the roof of a house, of a basement. This is insulation, usually fiberglass, some insulative material. And you can get this Home Depot, Lowe's, something like that, but it's the R factor. And very often the industry, the terms that they use, the quantities that they use in an industry are very different from the quantities, how we deal with them in a physics or an engineering class. And I'm showing you this now just so you might find yourself in a position, maybe even not as an engineer, but as a consumer, buying or making consumer decisions about insulation. And I just want you to see how it relates to what you're learning in your physics class. So the R factor, and I'm using this script R as the textbook does because I just want to make a distinction that it's not the R that you just learned about. This is a different R. So the R factor, I'll write it as a script R, describes a substance regardless of its area. The R factor is that R that I just told you about, the thermal resistance times the area. And it's equivalent to, here's the important part, it's the thickness of the material divided by its thermal conductivity. So when you buy some insulative material like fiberglass, you might buy it in a roll of the material. It is rated that how well it insulates from heat traveling through, how well it insulates, is its thickness divided by thermal conductivity. The units of R, or the R factor, are meters squared Kelvin over watts. In the United States, it's feet squared, degrees Fahrenheit, hours over BTUs. Now, I'll just let you know ahead of time, there will not be homework or test problems in this class related to this, but I'm just showing you how R factor works. So some insulating material, it might have R19. And what R19 means is that there's a loss of 1/19 of a BTU per square foot for each degree Fahrenheit temperature difference across the insulation. So for example, we have problem number 28. 28 says that a wall loses 0.040 BTU per hour through each square foot for each degree Fahrenheit temperature difference. And that means that 1 over the R factor is 0.040 BTU per hour, feet squared, degrees Fahrenheit. We'll just take the reciprocal of that. So the R factor is 25. It's an R25 material. And again, there won't be any more on that said in this class. Well, conduction is the first heat transfer mechanism. I'm going to talk briefly, very briefly, about the second one, and then a bit more about the third one. So there is convection. Convection is heat transfer due to fluid motion. And I won't cover it too much because the math of it is very difficult. The mathematics, it's just there's more than required than just the maybe 2 semesters of calculus you might have had. So in a more advanced physics or engineering class, you can get more into the math of convection, but here I just covered conceptually. The convection is a cause of much of our weather on Earth. So warm air rises, it gets less dense and it rises. Cool air gets more dense and it sinks. And so you have this churning up and down of air. This also is effective with blood circulation. One of the many, many things that our blood does in our bodies is it transfers heat from one part of our body to another. Our body does not, or inside our bodies, our human bodies, it does not conduct heat very well, but blood does a lot of the heat transfer. Let's go to the third mechanism, which is radiation. You look at the pictures down below, the electric stove burner and the incandescent light in the middle there. You turn on a burner, the stove, and it glows. It might glow orange. It's giving off heat. It loses energy by emitting electromagnetic waves, which we call radiation. And our sun also does that. These give off heat. It's electromagnetic waves, and it also, based on that heat that it's giving off, the electromagnetic waves, we see light. We see light of different colors. When we talk about the power radiated from an object, the radiated power increases rapidly with temperature, and this is known as the Stefan-Boltzmann law. Power equals E times sigma times AT to the fourth. Let's look at each of those things. Of course, power is joules per second, otherwise known as watts. E is the emissivity. We won't get into that too much in this class, but if you take a more advanced thermodynamic class, you'll explore that more. Emissivity ranges somewhere between 0 and 1, and it describes how effective the surface of the material is at radiating. 0 means it's a perfect reflector, 1 means it's a perfect absorber. We call that a black body. Sigma is a constant, the Stefan-Boltzmann constant. It's one of those useful constants in the front flap of your book, 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. And then there's the there's the area, the surface area of the material through which heat is radiating. And then temperature to the fourth power. So power is heavily dependent on temperature because of that T to the fourth relationship. Now, objects also absorb radiation from their surroundings. If it's cooler than its surroundings, then the same equation will go into effect. So we can say that for an object, P out, the power out, is E times sigma A T to the fourth. Power in is E sigma A times the ambient temperature, which is the temperature of the surroundings, to the fourth. The net amount of power radiated and the difference in temperature between the object and the ambient temperature, that will affect whether power radiates out or in. If the object is a hotter temperature than its surroundings, power will radiate outward. If it's cooler, power will radiate inward. And that goes back to the basic law that heat always flows naturally from high temperature to low temperature. So for the net power radiated, the rate of heat radiated, it's E times sigma times A times T to the fourth minus the ambient temperature to the fourth. Now, if we're talking about a very hot object compared to its surroundings, such as for the sun, the temperature of the sun is much greater than the ambient temperature, so T sub A is negligible, and we can just ignore it and go back to the original equation at the top of the screen. So with that, we can calculate the sun's power. We can say power equals E sigma A T to the fourth. We can assume the sun to be a perfect emitter, a black body. We'll just say E equals 1. Sigma times its cross-sectional area times T to the fourth. Well, for its cross-sectional area, we need the surface area of a sphere, so that's 4 pi r squared. You can look up in the back flap of the book. The radius of the sun is 6.96 times 10 to the 8th meters. Don't forget to square that. The temperature of the sun, this is the surface temperature. We can look that up in the back flap of the book. It says 5.8 times 10 to the third Kelvin. The amount that I gave, the quantity that I gave on the screen there, we can look that up, 5770 Kelvin. I'm just using that temperature because actually I'm looking in the book right now at example 16.5 and it's doing it backwards. Example 16.5 has you solving for the temperature, and that's what we get, 5770 Kelvin. So let's just use that number, and we get the power of 3.83 times 10 to the 26 watts. Another example, we can think about the evolution of the sun after it burns up in about, we expect maybe about 5 billion years. We expect that the sun will have used up all of the hydrogen that's in its core, turned it all into helium, and it will become a red giant. You can look at the picture down below. There's a red giant called Aldebaran, substantially bigger than our sun. So our sun is going to grow, we expect, many, many times its current size. It'll get cooler in temperature, and so it'll not be a yellow star anymore, but rather a red star, red from that cooler temperature. And we expect it'll be about 50 times its current diameter at a temperature of about 4,500 Kelvin. So let's think about, will it be brighter, will it be dimmer? So it'll be bigger, and you can think, well, bigger will make it probably brighter, but it's also going to be a cooler star, and maybe that cool temperature will make it dimmer. So these two variables are going to work against each other. But let's see how much brighter or dimmer is our sun as a red giant going to be. So we're going to set up a ratio, P1 over P0. So P0 is what its power is now. P1 is what its power is going to be when it's a red giant. So when we set up that ratio, we have E sigma A1T to the fourth. I should have written T1 to the fourth. And P0 is E sigma A0 T0 to the fourth. The E and the sigma, they divide out, and we're left with the area, 4 pi R1 squared, T1 to the fourth, over the initial, or the current area, 4 pi r naught squared T naught to the fourth. The 4 pi's divide out, and we're left with these ratios, r1 over r naught squared times t1 over t naught to the fourth. Interestingly, we don't really need to know what the current radius is or the future radius. All we care about is that it is a ratio of 50 to 1. So now we have P1 over P naught is that ratio, 50 over 1 squared, so 2,500 times. And now the ratio of the temperatures, 4,500 Kelvin over 5,800 Kelvin. I'm using 5,800 Kelvin as opposed to the 5,770 Kelvin that we saw in the previous example, just because 5,800 Kelvin is usually the number, rounded to significant figures, that's usually the number that's used in astronomy textbooks. And what we get is 905. So the ratio of the sun's power in the future to its power now is 905, which means it's going to be, we expect, 900 times brighter than it is now. That is the end of section 16.3 on heat transfer. Have a great day.